Hello and welcome to sections 19.3 to 19.4. In this video we'll be going over example 1, which looks at conservation of momentum for a planar rigid body. So previously for particles we had conservation of linear momentum, so we could model that as the sum of the L1 is equal to the sum of the L2. Remember where L is mass times velocity. For angular momentum, we're just going to get the sum of the angular momentum, so h naught or hg. So this could be hg1 and sum of the hg2. And if it's for about a point that's fixed or an instantaneous center, then we would just use h naught or h instantaneous center. So let's apply that problem, those equations to example 1. So example 1, we have this rod hanging down. It is currently not moving. Let me clean that up. We have a bullet over here, or a ball, or whatever projectile, and it's going to hit down here, 0.75 from the pivot point. We're going to figure out the bullet embeds into this rod, this wooden thing, and we're going to get some new velocity at the end, so the bar will be kind of spinning up this way with some omega 2. And our goal is to find that omega 2. So I've redrawn that here. So we're going to use conservation of momentum in this case. Again, conservation of momentum is we have no impulse. There's no external impulse. So we do have a transfer of energy or whatnot between these two. But if I kind of do like a boundary around the system, there's no forces into the system. There's no forces out of the system. So everything's contained within here. So the bullet hitting the rod, it's all contained, so we can neglect any impulse and just do our analysis. The equation we're going to use is the sum of the angular momentum about O, because we're fixed about O. We could do this about G, but it becomes a bit harder. So I've chosen to do it about O, just because we are fixed there. It'll make it a little bit easier. If I do it about G, then what I have to do is I have to find the reaction forces up here. I didn't draw those in because I wasn't planning on using them. But if you did it about G, you would need to find your reaction forces. Let's see here. We're going to assume that this is going to kick up this direction, so our omega 2 will be that way. So let's make our assumed positive direction the same way, so that counterclockwise direction. It'll make it easier for us. So sum of h naught at 1 equal to the sum of the h naughts at 2. So this is a summation. We do have two bodies. We have the projectile and we have the rod. So let's break this apart. So we will have h of the, it's a bullet, at 1 plus h of the rod at 1 equal to the h total. So this is, remember they embed, they get stuck together at state 2. So for states here this is time, so it's some time later, so it's after the impact. This bar starts off at rest, which means that we won't have any angular momentum in the rod. We will have the bullet. The bullet has an initial velocity of 400 meters per second. And so we could use mass velocity, but that's for linear. So mass velocity 1. To turn it into angular, if you remember, we then multiply it by d, and that's how we'll get angular momentum. So dmv. And we can only use the tangential portion of it. So we're going to have a portion of this that's downward and a portion of this that is rightward. So only the rightward portion is going to cause rotation. This downward will be in the direction. It won't create, if you think of it like as moments, it won't create a momentum about point O. So we also need to include the angle here. So that is cosine of 30 degrees. And then on the right-hand side, the h total is going to be I naught total times omega 2. Alright, so let's start filling in our numbers. So the distance that it acts is 0.75. The mass of our projectile is 4 grams, so don't put in a 4 here. It is 4e negative 3, or 0.004. The velocity is initially 400 meters per second. And we're going to use cosine 30 or root 3 over 2, whichever you prefer. I naught total is going to be I naught for the rod plus I naught for the bullet. And this is at state 2, and then omega 2. So I need to find this piece to finish. I'll go ahead and calculate the number for this side, just a second. Alright, that is 1.039. And now we can break these apart. So I naught for the rod, well, that's a slender rod about a fixed point. So if you go in the back of your book, you're going to find that we can model this as 1/3 m rod L squared. So 1/3 ml squared. For the projectile, this is going to be a little bit odd. So we know that it's I guess we're going to use, I'll write it out and I'll kind of explain what's going to happen. We're going to get IG, or I guess not IG. So IG for the bullet. We're going to use parallel axis theorem, mass distance squared. This is all for the bullet at state 2, and then we have omega 2. Fill in our numbers. The mass of the rod is 4. The length of the rod is 1. All right. So this is just standard parallel axis theorem. What we're doing is we're going to take the mass moment of inertia of a particle and move it up to our point O. Well, since it's a particle, it has no mass moment of inertia about its center of gravity. It has no size. But it is acting some distance away, so we will get that component. So this will be 4e negative 3. Our distance is at 0.75. We square that. Omega 2. And then all these are numbers, that's omega 2, so we can solve for omega. And you should get that it is our 1.039 from over here. This should total up to be 1.669. And you'll get 0.6225. Oops, 6. And that is radians per second. It is positive, which means that it is rotating the way that we thought it would. So that's omega 2. All right. So hopefully that helps. Again, just conservation of angular momentum. We work with a particle and a rigid body, and then we put them together. Remember, we can't add momentums unless they both act at the same point. The mass moment of inertia for a particle is 0, but if it acts some distance away, then you can use parallel axis theorem to move it to find what that is about some point that's not at that particle center of gravity, which would be the position of the particle. All right, if you have any questions, let me know.